All right, we're going to wrap up chapter 2 by taking a look at lesson 2.8 on analyzing graphs of polynomial functions. So to review, let's bring all these terms together and recognize that they all mean very similar things. Zero, solution, and x-intercept, pretty much the same thing. Zeros and solutions are what is the value that makes the function equal to 0. And we use factoring as a process to get there. It's one of the ways we can solve for our zeros. And then from there, once we know what the zeros are, we have to recognize that it means it's an intercept of the function and that graph intercepts through whatever the value is, k, comma 0. So when you're asked to find the intercept, the x-intercept, it is what is the ordered pair that is the intercept of the x-axis when y or the function is equal to 0. Let's take a look at our first example, and we're going to graph the function, and we can tell by looking at the graph that it's a cubic function because there are 3 factors, -3, +2, +2. Because x minus 2 is on there twice. And because it's a positive graph, it's going to go in opposite behaviors, and whatever x does as x gets more positive, y does as well, and as x gets more negative, so does y. So step 1, we're going to plot the intercepts, and then we're going to make a table of values of the points that are between the x-intercepts and beyond the x-intercepts. So really we should have a value on here for -4, but we did not. But that's okay because we know it's going to probably be going more negative anyways. So now that we have graphed the function, we can determine the end behavior, and we knew that it was a cubic function and it had the constant factor of 1/6, so that's positive. So again, as I said before, as x becomes more negative, so does y, and as x becomes more positive, so does f of x, so does y. So then we can draw the graph and making sure that it passes through those points that we have plotted and that it has the behavior we were expecting. So pretty easy. When we look at a graph such as a cubic function, this is not the exact same one we just looked at, but it's pretty similar. The turning points is when it turns and goes in the opposite direction, kind of like a vertex. And we call those local maximums and local minimums. So if the point is the highest compared to all the points around it, that's considered a local maximum. And a local minimum would be the lowest point compared to the points around it. We don't call it an absolute minimum or an absolute maximum unless no points, no y values ever go any higher than that point or any lower than that point. So most of the time we're talking about these as local minimums and local maximums. All right, and turning points. How many turning points should you expect? At most, it's going to be n minus 1. So whatever the function degree is, subtract 1, and that's the most number of turning points you're going to have. And if all of your zeros are real zeros, no imaginaries, then you're going to have exactly that many turning points. So if I have x to the 4th, that means I have 4 distinct, and I have 4 distinct zeros. That means I have 3 turning points. So at most, I would have 3 turning points. But sometimes we don't have that many turning points. It just gives you the most number to expect. All right, let's take a look at a function. We can ignore this because we've already seen that. Okay, example 2. So finding the turning points. So here are our 2 functions. Let's take a look at the first one. X to the 3rd minus 3x squared plus 6. So at most, we are going to expect 2 turning points and 3 solutions. So using our graphing calculator, we can plug in the coordinates and then adjust our window to be able to see what is going on with the function. So using the graphing calculator, we can determine that there's 1 x-intercept and 2 turning points. So use the solver function to figure out what is that x-intercept and what are the local maximums and minimums. So for the Casio, you would just hit F5 or Shift F5 and then root to find the intercepts, and F5 and maximum to find the local maximum, and minimum to find the local minimum. Very, very easy. And so the answer to this is that the x-intercept of the graph is approximately at negative 1.2, and the function has a local maximum at 0, 6, and a local minimum at 2, 2. Take a look at the second function. It should say g of x equals 5x to the fourth, so there is a minor typo there. So it's a quartic function. That means at most we are going to have 4 intercepts and 3 turning points. So use the graphing calculator to graph the function, and notice that the graph has those 4 x-intercepts and the 3 turning points that we expected. So let's use the graphing calculator to help us determine local minimums and maximums and figure out approximate values of the intercepts. So the x-intercepts are that x is approximately negative 1 and 14/100, negative 29/100, and positive 1 and 82/100, and 5 and 3/100. So most of the intercepts were positive there. And then the function has a local maximum at 1 and 11/100, comma 5 and 11/100. We can see that where it's between the two low values. And then the local minimums, the one on the left is negative 57/100, comma negative 6 and 51/100. And then the one on the right is 3 and 96/100, so almost positive 4. And notice that the y value is way down there at negative 43/04. So again, you're going to have to look at your values, and if you're not seeing all of the turns that you expect to see, and you're not seeing the end behavior, make sure you adjust your viewing window so you can find all of the points. All right, example 5, we're going to maximize a polynomial model. So arts and craft. You are making a rectangular box out of a 16-inch by 20-inch piece of cardboard. The box will be formed by making the cuts shown in the diagram and folding up the sides. You want to make the box have the greatest volume possible. All right, so how long should you make the cuts? What is the maximum volume? And what will the dimensions of the finished box be? So lots of things going on. Let's look at the picture. So we have a piece of cardboard, 20 by 16, and we are going to cut out the same value from each side so that we are able to make our box. Notice it's not open box. So volume is going to be length times width times height. So looking at the previous picture, we can see that the length was 20 minus 2x times the width, which is 16 minus 2x, times the height. When we fold it, the height would be x. So multiply all of that together and then factor out, well, don't factor out, but you can factor out if you want to in order to solve the equation. When we put it in that first form of the second line you see, 20 minus 2x times 16 minus 2x times x, that gives you your x coordinates, which is pretty nice to find, so your x-intercepts. So to find the maximum volume, we're going to graph the volume function on the graphing calculator. And of course, we only want to consider any physical dimensions from 0 to 8, because we can't have a negative number. And if I have 16 minus 8, 16 minus 2x, and x is equal to 8, then the width would be 0. So we can't have anything less than 0, and we can't have anything more than 8, because we don't want to have any 0 values. Okay, so then when we graph the function, we find that the maximum volume is approximately 420 when x is equal to 2.94, or approximately 2.94. All right, so we should make the cuts about 3 inches long, and then the maximum volume is about 420 cubic inches. The dimensions of the box with this volume would then be about x equaling 3 inches, that's your height, times 10 inches, which would be your width, by 14 inches, which was the length. So I would have actually written this as length times width times height, so 14 times 10 times 3, keeping with the previous way it was written, but this is also acceptable. And that is actually going to be it for our lesson. Again, lots of information here, so if you need to, go back and review this video, pause when necessary to copy down important information. I'll see you in class.